Welcome folks to this new tutorial video. In this video we're going to have example to show you how to solve for the step response for series RLC circuit. So when you solve for the solution of the RLC circuit, you end up with mathematical expression, and you need to graph this mathematical expression using Matlab. And once we do that, then we're going to simulate the circuit using PSpice OrCAD simulation, and we're going to compare the graph obtained from the PSpice simulation to the graph obtained from Matlab, and that basically will verify that our analytical solution to solve for the circuit is correct. So this particular example is part of a laboratory assignment here at Washington State University. So if you look into the circuit, this is the circuit we have. We're going to have a 5 volts voltage source. We're going to have some switching applied to the circuit. Now keep in mind that after switching, we're going to apply 5 volts to the circuit. And this is going to be implemented using a function generator. The function generator has internal 50 ohm resistance. We're going to count for it here because this 50 ohm resistor is relatively large compared to the resistance values of the circuit. So we're going to include that 50 ohm resistance for higher accuracy. What we measure in the laboratory is the voltage outside the function generator. We will never be able to obtain the internal voltage of the circuit when it is directly connected to the RLC circuit. So then we're going to have 470 ohm resistor connected in series, and here we have R2 is another 470 ohm resistor. Here we have inductor. This inductor is 1 millihenry, which has a nominal internal resistance of 2 ohms. This internal resistance is caused basically by the wiring, the conductor, where the conductor has some resistivity and thickness, cross-sectional area and length. So there is some equivalent resistance of this inductor that is connected in series of the inductance itself. Then we're going to have a capacitor. This capacitor is connected in series with the inductor. And then to measure the current through the inductor IL, to measure the current using the scopes, we decided to add a 10 ohm resistance that is in series with the inductor. And this resistance, we call it R-sense. So when we measure the voltage across this resistor, it is basically 10 times IL. So this circuit is built for a laboratory assignment, experiment basically in the lab, and the students need to build it and verify the solution to the circuit. So the capacitance value here going to be 100 nanofarad. So this circuit gonna be basically overdamped circuit. We're gonna go through the solution to show you that. But in the lab, they're gonna apply 100 nanofarad, and then they're gonna come back and change it and make it 1 nanofarad, and they're gonna see the difference between the overdamped and the underdamped circuit, because when they apply the 1 nanofarad over here, it's gonna be an underdamped circuit. So basically, we're gonna solve for the circuit. This is the pre-lab assignment, is to solve for the circuit analytically, then graph that analytical solution and compare it with the PSpice simulation. So students need to do that before they come to the laboratory. Here is the steps for solving RLC circuits. The first one is basically you need to determine if this circuit is parallel RLC circuit or series RLC circuit. And once we do that, we need to determine what's alpha and omega naught and calculate the roots S1 and S2. So the first thing we're going to do is we're going to draw the circuit right after switching and suppress all the independent sources. And then we're going to combine all the resistors into one equivalent resistance. So it is crucially important that to have one equivalent resistance, one equivalent inductor, and one equivalent capacitance to use the steps that we are applying here. So when we apply this step, basically we know that after switching, this is short, the switch is short at 0 plus, and then here we're gonna have basically this voltage source gonna be suppressed, so we're gonna make it short circuit. So we're gonna have here the 50 ohm resistor is in series with the 470 ohm resistor. This can be combined into one resistor, and then those two resistors combined into one will be in parallel with R2. The equivalent of those two going to be in series with the 2 ohm resistor, which is in series with the 10 ohm resistor. So basically all those resistors going to be combined into one equivalent resistance. the equivalent resistance is going to be in series with the inductor, which is in series with the capacitor. Clearly that this is a series RLC circuit. In fact, that is so intuitive because you can see that the inductor is in series with the capacitor, and those resistors can be combined into one equivalent resistance. So what we need to do, we need to find R equivalent, and R equivalent for the circuit, as stated earlier, it's RS, that is in series with R1. The equivalent of that going to be in parallel with R2, which is in series with the internal inductor resistance, which is in series with R sense. So when you plug in the values into your calculator, you will find that R equivalent to be 258.87 ohms. So we were able to find R equivalent. Now we can solve for alpha. For series resistance, alpha will be R over 2L. When you plug in the values for R equivalent and 2 times 1 millihenry, that's the value for the inductor, we have alpha to be 129,435. The unit here per second, 1 over second. So it's a large number, but that's okay. It's basically a very fast circuit. It's a fast circuit. It changes with time fast, kind of. And then when we force C equals 100 nanofarad, we gonna have omega naught to be 1 over square root of LC, and this gonna be basically 100,000 radian per second. So from here we can solve for S1. S1 will equal to minus alpha plus square root of alpha squared minus omega naught squared, and this will give us this number, which is negative 47,256. Now we can solve for S2, which is minus alpha minus the square root of alpha squared minus omega naught squared, and this number is going to be even a more negative number, which is minus 211,610 per second. So now we know that the solution to the system going to be overdamped, and if we solve for IL of t, we know that IL of t will be A times e to the S1 of t plus B times e to the S2 of t plus IL at infinity. This is valid for t greater than 0, right after switching. And if we solve for VC of t, we're going to have VC of t will equal to C times e to the S1t plus D times e to the S2t plus VC at infinity, where A, B, C, and D are constants that depend on the initial conditions. The solution of IL of t or VC of t, we need to find IL at infinity, VC at infinity, and we need to apply 2 initial conditions to find A and B or C and D. So here we need to find IL at 0 and IL prime at 0, and we need to find VC at 0 and VC prime at 0 to solve for C and D in the second case. So let's show you how to do that. So the first thing I'm going to do is I'm going to basically find IL at 0 and VC at 0. So we're going to draw the circuit before switching, and before switching the inductor is short circuit and the capacitor is open circuit. So this is the circuit we have before switching, that the switch basically was connected short. So the switch was basically short. We have the 50 ohm resistor here, the 470 ohm resistor, 470 ohm resistor here also. The inductor going to be shorted, which is this inductor shorted, and the capacitor going to be open circuit. So clearly, because the capacitor is open circuit, IL will be 0, and because no source to the circuit, also VC going to be 0. So this is very intuitive. IL is 0 amp and VC is 0 volts. Now we need to find IL prime at 0 plus and VC prime at 0 plus, basically the second initial conditions. And to do that, we need to draw the circuit right after switching. We need to force IL at 0 and VC at 0, and then we need to solve for IC at 0 and VL at 0, of course right after switching. So we're going to say at 0 plus. So let's draw the circuit at t equals 0 plus right after switching. Now what happened is the 5 volts have been applied to the circuit. The switch is shorted here. We have the 50 ohm resistor, we have the 470 ohm resistor, the other 470 ohm resistor. Here is our inductor, and the current through this inductor is 0, so I'm forcing 0 amp through the inductor. This is the 2 ohm resistor. This is the capacitor, and I'm forcing 0 volts across the capacitor. And then we have our sense, right? So this is the circuit right after switching. So clearly that we know that IC at 0 plus is going to be 0, because this current, that is the inductor's current, is continuous, and that inductor current is 0. That means IC is 0. So we can say that IC at 0 plus equals 0 amp, and this is given to us. So now we solved for IC at 0 equals 0. We can say that what's VC prime at 0 plus, which is the derivative dVC dt at t equals 0 plus is. It's basically IC at 0 plus over C. And since IC at 0 plus we found it to be 0, then the derivative is going to be 0. So here we end up solving for the second initial condition for the voltage across the capacitor, and that is basically 0 volts per second. Now we need to solve for the second initial condition through the system, which means that we need to solve for VL at 0 plus. Now to do that, we need to be a little bit clever. We know that IL is 0 at 0 plus. That means the voltage across the 2 ohm resistor is 0, and the voltage across the 10 ohm R sense resistor is also 0. So if we do KVL here, we can state that V2 will equal to, by KVL, VL plus 0 plus 0 plus 0. Basically, VL will equal to V2. Those two voltages are equal. Also, the second trick is that since the current here is 0, the current through the inductor is 0, at t equals 0 plus, then the current will circulate within this loop. That means those resistors going to be basically in series, right? Because the current goes through the 50 ohm resistor is the same as the current go through R1. Since the inductor's current is 0, then all of that will go through V2. So we know that V2 equals to VL. Now I need to solve for V2. So to solve for V2, it will act as a voltage divider because those resistors act as they are in series, basically through KVL. So we can say that VL at 0 plus will equal to V2 at 0 plus, and using the voltage divider, it's going to basically be R2 over RS plus R1 plus R2 times the total voltage, which is the 5 volts. When we solve for that, this is going to be 2.373 volts. We solved for the voltage across the inductor right after switching, and from here we can solve for the derivative of IL. So we can say that IL prime at 0 plus will equal to DIL dt at 0 plus is basically the second initial condition. That is VL at 0 plus over L. When we plug in the value, we have 2,373 volts per second. So we solved for the two initial conditions. Now we need to find IL and VC at infinity. And to do that, we know that at infinity, the inductor is going to be short circuit and the capacitor going to be open circuit. So we draw the circuit after switching for t equal infinity, going to be after switching, and then the inductor is shorted and the capacitor is open. This is the circuit. So what we're going to have here is the 5 volts, and then this is going to be shorted. Then we're going to have the 50 ohm in series with the 470 ohm, which is in parallel with that. The inductor is shorted, capacitor is open. Basically, we transfer this circuit into that, make sure that after switching, and we make sure that the inductor is shorted and the capacitor is open. Now, when you look at it, at t equals infinity, the inductor current going to be 0 because the capacitor is open circuit. So this is your IL, so your IL going to be 0. It's clearly to see that. So we can state that IL at infinity will equal to 0 amp. However, for VC, it's not going to be 0 because now we can say that at infinity, V2 will equal to VC because the inductor is short. The voltage here is 0 and the voltage here is 0. So by applying KVL here, we can say that V2 equals to VC. But also, we know that since the inductor's current is 0, then all of this current through RS and R1 will go through R2. that means that the current will circulate within the first mesh, and we can apply the voltage divider to find V2, which is basically VC. So we can say that VC at infinity will equal to V2 at infinity, and VC at infinity basically will be using the voltage divider, R2 over RS plus R1 plus R2 times the 5 volts, which is the 2.373 volts. Now that we found the voltage across the capacitor at infinity and the current through the inductor at infinity, we can plug in those values to solve for the coefficients. So now we can apply the initial conditions to solve for IL of t and VC of t. So we know that IL of t will equal to A times e to the S1t plus B times e to the S2t plus IL at infinity. We know what S is. We know what S1 is and what S2 is and IL at infinity. So we can plug in those values, and now we're going to force the first initial condition. That basically means that IL is 0. Now when we apply t equals 0, this becomes 1. E to the S1 0 is 1, and e to the S2 0 is 1. So you're basically going to say that IL is 0, which found to be 0, will equal to A plus B plus IL at infinity. So here we know that A plus B equals 0. So this is the first initial condition that we have, A plus B equals 0. Now I'm going to apply the second initial condition, and I will say that the derivative IL prime at 0 will equal to, when you take the derivative, the S is going to come here. So you're going to have S1 times A, and e to the S1 at 0 is 1. So you're going to have S1A, and here you're going to have S2B. And we know that the derivative of IL prime at 0 plus is 2373. So, and we know the value of S1 and we know the value of S2. So now we have the second equation for A and B. So now we have two equations, two unknowns, and now we can solve for the constants A and B. So I end up solving for A and B to be 14.4 and minus 14.4 milliamp. So IL of t will be 14.4 times e to the S1t minus 14.4 times e to the S2t in milliamps. I solved for IL of t. Now we can do the same thing for the VC of t. We know that VC of t will equal to C times e to the S1t plus D times e to the S2t plus VC at infinity. So we're going to plug in the values. We know that at t equals 0, VC was 0, and then this becomes C, this becomes D because e to the 0 is 1, and VC at infinity was 2.3. So from here we can say that C plus D will equal to negative 2.373. This is the first equation for finding the constants C and D. Now we're going to apply the second initial condition, which is the derivative of V prime C at 0 plus. And when you take the derivative of VC of t, that's going to be S1C plus S2D. And this is basically a 0. So we're going to have, we know what's the value of S1 and S2. So basically the derivative, which is 0, will equal to S1C plus S2D. This is the second equation we have. And now you can basically solve for C and D. We found that C will equal to negative 3.06 volts and D was plus 0.682 volts. And we know that VC at infinity is 2.373. So this is basically VC of t. So this is the solution for the series RLC circuit that we have. At this point, I only know the equations that describe IL of t and VC of t. And to validate my solution to the PSpice OrCAD solution, I need to graph IL of t and VC of t, because OrCAD PSpice will show me the graph of IL of t and VC of t, will not give me those values. So I need to graph those, the equations I obtained, and I will do that basically using Matlab. So let's load Matlab and write a script to show you how to plot those values. So here is the Matlab script that I have created. Basically, you create a new file and you enter this script, and that will basically graph the solution that we have. So in the first line, basically I use the unit prefixes nano, milli, and micro, just in case if you need them. I entered the values. In the second line, I entered the values of L, 1 millihenries, C is 100 nano, and what's our equivalent was, which is 258.87. I found alpha, I found omega naught, right? Those basically to validate if my answers were correct or not. Then I calculated what's S1 and S2 is, basically minus alpha plus the square root of alpha squared minus omega naught squared, or minus alpha minus the square root of alpha squared minus omega naught squared. Then I need to define a vector that defines the time. So here I'm simulating my time from 0 to 2 millisecond with a step size of 10 nanosecond. And then I enter the equation for IL, and I'm going to plot IL. I will show the grid, and I will show the minor of the grid, basically to make my graph look easy to visualize and see. Then I create a new figure, so I will have two figures, and then here I'm gonna basically define V of C. This is the expression for V of C that I have, and then I'm gonna plot V of C versus T, and I will have the grid on and the minor is on. So this at this level we provide the code for the students to use. The only thing they need to do is basically to plug in the equations or the solution, and they will be able to graph the function. And now let's run the script. So I'm going to run the script, and I'm going to have two graphs coming up shortly. So this is graph 2 and this is graph 1. So graph 1 is basically I of L. As you can see that IL will jump all the way to around 7.3 milliamp, and then we'll drop down to 0 again at infinity, because starts at 0, will go to some peak value, and then drops to 0 again. So this is the shape of IL. And for the voltage across the capacitor, this is the solution. We started at 0, and then it will kind of ramp up until it hits around 2.37 volts at infinity, right? So it ramps up, right? And here you have two time constants. It's just one of them is much faster than the other one. So S2 will die much faster, and then S1 will become more dominant. Anyway, so this is the solution. You can see that starts from 0 and will end up around 3.37, a little bit less than 3.4 volts at T equal infinity. Now what we're going to do is we're going to simulate the circuit. So let's load OrCAD and see what we have. So here I have created a new project, and I have draw the circuit. I would assume that you know how to draw the circuit. If you don't, you can watch previous videos. We have several tutorials on how to obtain the circuit. But what's important here is that we're going to use a rectangular pulse to simulate the step response. Let me zoom in so you can see it a little bit more. So let's look at the voltage source. So in the voltage source here, we start at 0, then we're gonna jump to 5 volts. We're gonna have some delay at 10 micro. This is just to make you see the rectangular pulse as you apply it at 10 micro. We're gonna have a very sharp pulse, so it will take 1 nanosecond to rise, 1 nanosecond to fall. We're going to have the pulse width to be very long, like 1 second, and it will stay for 5 seconds. It will stay at 5 volts for a whole second. Of course, we're going to simulate the circuit for much less than that. It's going to basically be 200 microseconds. Then we connected the rest of the circuit. I have R1, which is the 50 ohm. This is basically the function generator that we use to build the circuit. We have 470 ohm and 470 ohm here, 1 millihenry. The 2 ohms that are internal to the inductor, I have 100 nano, and then I have here the 10 ohms, which is basically the sense resistor. Now we're gonna basically define the simulation. So I'm gonna show you the simulation we have. So here we're gonna only simulate for 0.2 millisecond, which is 200 microseconds, and then we're gonna use the maximum step size to be at 10 nano. We're gonna apply, we're gonna say okay, and then that's basically what we have. I'm gonna start basically by measuring the current. So I'm gonna measure the inductor's current. I'm gonna measure the current at the inductor. So I will add the current probe over here to measure the current through the inductor, and then I will say run. So the simulation is running now. It will take some time until we get the graph. Here we go. So here is the graph. You can see that the inductor current starts from 0 at switching time. Here the switching time is 10 micro. Starts from 0, and then it will jump to a little bit over the 7. It's around 7.3 milliamp. That's the peak value. And then we'll drop down back to 0 again. Right? So this is basically the same as what we have in Matlab. So let me show you the figure in Matlab. This is the figure we have in Matlab, right? Starts from 0, and then it will go to roughly around 7.3 milliamp. So clearly, if you see the graph we have in Matlab versus the graph we have from OrCAD, it's the same. It's very almost identical. That means that our solution is correct, because this graph represents our solution. This graph represents the circuit simulation. Now I know that my graph and my solution are basically valid. Without doing this step of graphing the graph using Matlab or any software and comparing it with the circuit simulation, it will be very hard for us to validate that our analytical solution was accurate. And then now what I'm gonna do is I'm gonna basically plot the voltage across the capacitor. So what I will do is I will take this differential voltage. The differential voltage will start at the top of the capacitor. This is called V+, and then at the bottom of the capacitor. And I'm gonna basically view the simulation. So I'm gonna click on this button. And you can see that this is what we have. You can see that early on you have the two time constants are taking effect as the voltage across the capacitor starts from 0, but then eventually that S1 starts to be more dominating because the slower time constant, S1 is a slower time constant. And then we see that at t equal infinity we haven't reached the 2.4 yet. We're a little bit less than the 2.4. So let me show you that with the figure that we have from Matlab. This is the Matlab figure. You can see that it was kind of the two time constants are having an effect early on, but then the first time constant became dominating. It never reaches 2.4, right? This is basically 2.37. That's what we have here, 2.37. So now we know that our analytical solution to find VC is accurate because it matches our PSpice OrCAD simulation. So what I want to do next is I'm just going to come to the OrCAD simulation, and here I'm going to change this capacitor to make it 1 nanosecond, because this is the second part of the lab, is to change this capacitor to 1 nanosecond. We're gonna simulate the circuit, and when we simulated the circuit we can see that we have this effect. So this is basically the underdamped circuit, and here this frequency here is the oscillating frequency, here is the natural frequency. So if you wanted to know omega n, measure the time required from one peak to the second peak. What's the time required to go from one peak to the second peak? And then take the reciprocal of that and multiply it by 2 pi. So 2 pi over the time required from one peak to the other peak will give you omega n. Another thing is we are interested in is the overshoot in percent. If you take this peak value over the settling time voltage, so what's the peak voltage, over the settling time voltage, the voltage at infinity, times 100% will give you the overshoot. The overshoot is another important parameter that the students will calculate in this lab as well. So I hope you liked this video, and it's a very good tutorial for you to see how to solve for RLC circuit. And to validate your solution is correct, you need to simulate that circuit in OrCAD and compare the graph you have from Matlab with the graph you obtained from the PSpice, and this will validate that your solution is accurate. So I hope you like this video, and good luck to you. Thank you very much.